calculus friends, and this is going to be your second video about concavity and its consequences and how to find it. Previously to this, you learned that concavity is when the second derivative has a certain sign. So when your second derivative is positive, it's concave up. If your second derivative is negative, it's concave down. And at the places where your second derivative changes sign, there's a point of inflection. Now, quick note, if your second derivative changes sign, but it does so like a whole or an asymptote, that is not considered a point of inflection. You need a point on the curve for that to work. So now let's talk about points of inflection and intervals of concavity. I'm not going to read through the steps here. If you want to find the intervals on concavity, you want to find out when the sign of f double prime changes. Okay? Easiest way to figure out when a sign changes or doesn't change is to set it equal to 0 or find out where it doesn't exist, or maybe both. So in number 1, it says find the intervals where this function is concave up and or concave down. So I am going to take that function and I'm going to find its second derivative. So g prime is, let's see, that's going to be negative 6x squared plus 12x. And g double prime is going to be negative 12x plus 12. If I want to know when I change concavity, I want to figure out when the second derivative either equals 0 or does not exist. And let's see, that's going to be when x equals 1. That's when it equals 0. It always exists, so that's not really helpful. So my intervals of concavity are based on the original domain. Well, that's a polynomial, so my original domain is negative infinity to infinity. And I'm going to pause that domain at 1. So negative infinity to 1, 1 to infinity. Intervals of concavity are always open intervals. They are never closed. When it comes to intervals of increase and decrease, calculus-wise, we usually close them, but I've seen it both ways. Concavity, though, can never be closed. Don't close it, all right? So here's my two intervals of concavity. Let's figure out what kind of concavity it has. So in between negative infinity and 1, I have 0. So let's find the second derivative at 0. So here's my second derivative. If I plug 0 in for x, I get 0 plus 12, which is positive, which means g is concave up on the interval from negative infinity to 1. From 1 to infinity, let's use the number 2, g double prime of 2. Again, I'm going back here. Negative 12 times 2 is negative 24, plus 12 is definitely negative. G double prime of 2 is negative, which means g is concave down. So there's my intervals. Now I look at that and I realize my concavity changed, which means in between those two intervals of concavity, I have a point of inflection. So at x equals 1, and let's see, what would y equal? Negative 2 plus 6 minus 3. So negative 2 plus 6 is 4. 4 minus 3 is 1. So at 1, 1, we have a point of inflection because g double prime changed sign. Not so bad. Now, this is an important thing. It says just because the second derivative equals 0 or doesn't exist, you are not guaranteed to have a point of inflection. Points of inflection are where the concavity changes, where your second derivative changes sign. That means I couldn't care less what the sign or value of the second derivative is. At a certain instance, all I care about is, did it change there? Okay? So let's come down here and talk about that. It says state the coordinates of any points of inflection for g of x equals x minus 2 to the 4th minus 9. All right, so if I want points of inflection there, I want to know where g double prime changes sign. So g prime is 4x minus 2 to the 3rd times the derivative of the inside. That's just 1. So 4x minus 2 to the 3rd. And then g double prime of x is going to be 12x minus 2 squared times 1. All right, and if I want to figure out my intervals of concavity, I want to know when 12x minus 2 squared equals 0. That's going to be at x equals 2. So my intervals of concavity are negative infinity to 2 and 2 to infinity. If I find g double prime of 0, 0 minus 2 is negative 2, but squared is positive. So G is concave up here. And then if I find like G double prime of 4, 4 minus 2 is positive, squared is still positive, times 12 is still positive. G is concave up here as well. That's concave up twice. Did the second derivative equal 0 in between them? Yeah. That's not a point of inflection because my concavity did not change. Just to drive home the point here on number 3, it says state the coordinates of any points of inflection for H if H double prime is this monstrosity. Okay, well, points of inflection are going to be when the second derivative changes sign, which is when the graph of the second derivative, so if H double prime changes sign, oh, I can't write, sign, then H double prime crosses or hops over, in case you have a case where H double prime didn't exist, crosses or hops over the x-axis. Now, this H double prime is a polynomial, so it's not going to hop over anything. Its domain is everything. So in this case, I want to know for which of these values is H double prime going to cross the x-axis. So H double prime has a 0 at 0, 2, 5, negative 4, and 8. But a lot of those have even multiplicities, which means H double prime is going to bounce off the x-axis rather than crossing through it. So it would be at x equals 0, 5, and 8. Those are all points of inflection because H double prime would cross the x-axis. And that, my friends, is how you find intervals of concavity. That's it. That's all I got. Sweet. So I hope you are all having a glorious day, and I will talk to you again soon.